Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And in keeping with the systems theme, I'm pleased to introduce Brendan Murphy, who's going to tell us something about humans and systems research.
People don't know me. I'm Brendan Murphy. I work in the lab looking at the relationship between how code is developed and how it fails in the field. And I just wanted to do a sort of more light-hearted view of the biggest issue affecting systems research. Systems research is sort of very focused on technology. And you propose things and say it's going to make a 10% improvement in a certain attribute. And it never does, and the basic reason is humans. And it's not just end users, it's humans, any human in the development chain. So I want to just go through some of the issues around this. What I do today is look at some work I did in digital, which is looking at reliability. And one of the problems we first looked at there was the fact is that the theory of how things are supposed to work and reality are two completely different things. And at some point in time, you have to sort of realize that the reality is correct and the theory may not be correct. When I was in DEC, we actually then moved from blaming hardware to be the cause of reliability issues to software, because it has to be some technology reason. And again, we found that wasn't quite the case. And then every time we actually think we're able to characterize these things and build the sort of human aspects into the system behavior, they manage to undermine our work. And I'll give some examples of that. I then moved to Microsoft, and I started looking at the way software is developed. And you really sort of, as a systems researcher, you really prefer to focus on technology. It's a much easier thing to do. And so we focused on technology, and yet again found that you couldn't just focus on technology, you had to take these sort of pesky human assets into account. And so finally, we're sadly having to embrace the human element in a reluctant manner. So I'll go through what we're doing there. When I was in DEC, I took over a program which actually monitored systems in the field. By using the phrase DEC, that immediately ages me. People know it as DEC, people may know it as digital, and people may never have heard of it, sadly. We collected data from systems using a fancy network called a telephone. The computers used to phone out back to the service centers, and it used to dump a lot of data back to us. And these were event logs. And I took over the program that was running this. And basically, hardware reliability has a gold standard of how you measure reliability, and that is the bathtub curve. The bathtub curve is basically when you get a new piece of hardware, you have a period of early life. The early life is due to manufacturing errors or possibly back-related issues with components. It then reaches steady state, and then you have a wear-out phase. Everybody, all papers at that time, all basically defined reliability based on this model. There was a paper from somebody in tandem who actually identified that about 50% of tandem failures were due to human elements, but everyone else used this model. And to this day, you actually see an awful lot of hardware reliability models which are based on the bathtub curve. And I defy anyone to find any computer which has ever failed in a bathtub curve-like way. But because we were new to an area and everyone says the bathtub curve is true, then the bathtub curve must be true. So we're actually able to fit the data we collected from customers onto the bathtub curve. We didn't really want to buck the trend at this stage. But to do that, you had to sort of manipulate the data. One of the first things we found is that actual crashes don't occur in isolation. And yeah, this is to this day. About 80% of crashes will occur in isolation. The other 20% of crashes will induce further crashes. And they can actually be quite dramatic in how long it takes for the system to stabilize. That skews the data. So what we decided to do was, well, we're looking at reliability, and these secondary crashes are recoverability, so we'll just ignore these clusters of crashes because they're not really reliability issues. Obviously, the customer doesn't have this benefit, they actually have all the crashes, but we can, statistically, we can remove them. Then what we found was that the old statistical classic, which is commonly called lying, is you group things together in big enough areas so that when you actually see underlying trends which you can't explain, if you group them into big enough buckets, then you can get rid of those underlying trends. And the other thing we did was we only counted crashes, even though at that point we actually did realize that crashes only contributed 10% of all outages on the system. Now, from an end user's perspective, they don't really care less what's bringing the system down. But we're system people, so therefore we care what brings the system down, and we'll only count the crashes. And if you can look at this slightly skewed, you can maybe just about see that the histogram, this is from old papers, but the bars are the crash rates. And as you can see, the crash rate maybe sort of just about comes into steady state failure rates here with, you know, a bit of imagination. This is a big problem. This basically says the really old machines are very reliable. Well, we ignore that. The other issue you have is this. This is reboots. And basically, across the life cycle, the machine gets better, improves with age. Thankfully, when early in my career in digital, we met the guy who wrote the tandem paper, which is Jim Gray. And we compared the behavior of machines in tandem and the behavior of machines in DEC, and we got very similar behavior. And the thing that Jim taught me was really, you know, if it looks like a duck and it quacks like a duck and walks like a duck, it's a duck. And I think is that you have to trust the reality of life and not the theory of how things are supposed to behave. So one of the first things we actually realized is that the way systems reliability works is it's actually time-driven. Not technology-driven, but time-driven. Unfortunately, we couldn't get, I don't think this is in any papers, but believe me, this data is true, is that the failure rates during the day is roughly this curve. It's basically you have a number of failures at midnight. The system becomes very reliable at 3 o'clock in the morning. Failures start happening, then you have lunch, and then failures happen. We collected data from all around the world, so in Italy that was actually a bit longer. The failures at midnight was because what would happen is everyone bats things for tomorrow morning, which is actually the 0 hours. And of course that was also the time you did backups. And there's nothing like compute-intensive programs and backups happening simultaneously to cause the whole system to hang, or to appear to hang. Now this would sort of, we also looked at NT systems in Unix. Unix was in universities, and literally it's the same graph but shifted 2 hours. Now you then say, well, this is obviously workload related, not usage time related, but you then say not only is it daily patterns, there's weekly patterns and monthly patterns. The monthly patterns override the weekly patterns. Monday's the worst day, like everyone else, like humans, and it goes well till the weekends. Basically, if things go wrong in the weekends, then you only find them out on the Monday, which is when things go wrong. But these are back-end systems, usually running manufacturing sites. Manufacturing sites are very back-end loaded onto the end of the month. And so at the end of the month, the last thing the system manager will ever do is to reconfigure the system. So in the back end of the month, no activity happens, and then at the start of the next month, you have to then do all the stuff you didn't do at the end of the month. So the start of the month is very unreliable, the end of the month is reliable. And then you can look at the year, and the year changes. December is by far the most reliable time of the year. The system manager will never reconfigure anything in December because they want to enjoy their Christmas holidays. They don't want to call it. So they defer everything from Christmas to January. January is the worst time of the year. Also, July and August is very good as well because they don't want the holidays ruined at the same time. And we saw these sort of commonality things that was happening. Some of them was called religious reboots. Basically, these were heavily, well-trained system managers with well-trained field people. And of course, when a system crashes, they're supposed to diagnose the system. No, they reboot it and pray to their God that the thing comes up again. And if it doesn't, then they diagnose it. Or they may try a couple of times just to make sure. Still happens today. Quite often a reboot will fix the machine. Sad but true. Urban myths. If people believe a certain thing will crash computers, it becomes a self-fulfilling prophecy. So when you actually found that a certain batch of memory components was bad, the last thing you'd do is tell anyone. Because what would happen is every computer in the world will crash due to that memory component. The other thing is system managers haven't, even today, they're out by a factor of 3 about the frequency of failures and reboots on their machines. They can remember 3 weeks ago the machine crashed due to a hardware failure. The 25 crashes that happened between then and now due to reconfiguration, they can't remember those things. Users can, system managers can't. So if you actually want to look at reliability, whatever you do, don't ask the system manager. So, and there's a number of practical reasons that we see affecting reliability. The classic one is that we initially ignore fault management and logging. Whenever you bring out a new product, you test it out, you do all the characterization of the product, you think you know it, it goes in the field, it then starts failing in completely different ways, and then you suddenly realize you have no idea what's happening in the field, and so what happens is you retrofit failures, which means the next release is just actually retrofitting logging and fault management, and then on the third release you can actually start fixing things. Also, we focus on failures. So if you actually find if a lot of crashes are due to something happening, then you will immediately stop that thing happening. What you don't ever consider is that thing, only 1% of times that thing happens actually causes a crash. So by stopping it happening, you now annoy 99% of people. Example, that's the Windows 2003, they put a memory check on tags. They had to fix it. They realized they had to fix it within 2 hours of release. Because even though some people were writing things in the wrong area of the address space, they then found out that phenomenal people's writing having no effect. And so they had to actually remove the thing. So quite often fault management is a curse as well as a blessing. We often ignore practical solutions. CERN were a major customer of DEC, and they announced that they actually had improved the reliability of their systems by a factor of 2. They sent a full team of people to see what was happening, and they actually put a cover over the power button of the disk systems. When they actually went to see why did they do that, they explained that they have all these disks in these rows, and when they bent down to fix one of the disks, the backside would power cycle the disk behind them. Which everyone thought was funny. The problem happens to be is we didn't do anything about it. And if you remember the first workstations were under the desk, you would remember you moved your chair into the desk and the first thing would happen, you'd power cycle your machine because your knee had just kneed into the power button. It wasn't too bad because you were in so much pain that you never noticed the power cycle. The other thing was quite interesting. We saw compact servers coming at that time. And we did a teardown on DEC, which is now called Digital, rebranding. And they actually realized that the technology within the compact servers was complete rubbish compared to ours. So everything was fine. The problem was compact actually had hot swappable power units and hot swappable disks and fans. Now for a DEC server, you had to remove the CPU to fix the fan. Whereas on the compact, you just flicked it and took it out. Now the fan broke 3 times as often as the CPU. So what compact were doing was simply saying, well, actually, why don't we just fix the stuff which is always breaking? And at that point, you actually then saw they had the right idea. They were actually fixing what was really causing failures in the systems, whereas we were fixing the technology, which is far more interesting. So, but it was becoming obvious that the way hardware behaved and the way the system behaved was different. And so obviously if it's not the hardware, it must be software. And we then started focusing on software. And when we actually looked at software reliability, then the thing that we noticed was that it's release-based. So basically, the first week or the first month of a release of an operating system is the most critical stage. That's when most failures are going to occur. Also, it's when the reputation of an operating system is made. Vista, in steady state, was as reliable as XP. But because when it was installed, it was so much problems, the perception is it was rubbish. And I think is that that's still today. Also, how long you delayed from installing the operating system. What this shows is that if you leave it 6 months, then you improve 25% the quality of your installation. when we've actually redone this and looked at other software, and this has nothing to do with technology, it's to do with knowledge. Basically, when failure is deterministic, if somebody says, whatever you do, don't run Fred on Windows 7, then you don't run Fred. It doesn't make it more reliable, it's simply you avoid the failure. And so this improvement actually is a natural improvement. So all operating systems will see that improvement, which is, some product people get upset about this because they actually claim it's all their patch release system. It's just knowledge that's passed on. So after doing all of this work with operating systems, we worked on a long time, we worked on 3 operating systems, Unix, NT, VMS. We actually came up with characterizing it. And this is very important because one of the things is that there was a massive logistical operation to try to support these machines. So you needed to know the relative reliability. And so we came up with this great measurement methodology. We spot the quality of the product as early as possible. And then humans still manage to mess it up. So here's an example. This is, again, difficult to read, but basically this is minor releases. That's it. Reliability is going this way. You have a minor release, then you have a major release, then minor releases, and things improve. So basically from 5.5 to 5.5.2, things got better. From 7 to 7.1, things got better. But there's an exception here. 6.0. 6.0 was the biggest load of rubbish DEC has ever produced in VMS. It had network capability, but it was stunningly bad. But our measurement says it is the very best operating system release they've ever had. So we went back to the field and said, you know, why is this? Why are we interpreting things? And they said, yes, it is really bad. It's so bad, we have to really plan the installation of the operating system. So we spend weeks planning the installation, and then we install it. And then the system managers know it's really bad, so they're really careful when they manage the system. So, and everyone says, oh, that's great then we don't get that bad a fact. But one of the things they miss is the fact is that they can achieve this level of quality, not through technology, but through managing the system differently. And it never sort of clicked to people that, well, maybe we should make it this easy to manage it, and then we'd improve the reliability of each operating system. But that's not system engineering, so we don't bother doing that. And we're actually very slow learners. Going back to the thing of putting a plastic cover on systems, RAID systems. Biggest cause of failure of RAIDs is the fact that you get a red light, it's 3 o'clock in the morning, somebody goes to swap the broken disk out, they're very bored, they swap out the disk next to the broken disk, you now get 2 failures and the RAID collapses. We don't have anything physically stopping them doing it, but we have 25 different versions of RAID, technology-wise, but nobody puts that little plastic cap on the RAID system to stop them pulling out the wrong disk. ECC is a non-deterministic type error, and the way we do with non-deterministic, so you get an error, but you don't know it's an error, it may not be an error. And traditionally the way we do this, even though we've got years and years of knowledge of how to handle hardware, when we actually get these complex errors, we decide we'll just give the information back to the system manager and expect them to figure out what's going on. And funny enough, they never do the right thing. And you either end up with far too many memory boards returned or not enough memory boards returned. And then every 5 years, we seem to come up with the same discussions on ECC, which is how do you handle the ECC errors? Should you suppress them? Should you interpret them? So we never seem to get to the point of knowing what to do. Cascading failures. We still have a situation where 30% of outages occur in these clusters. What technology has given us, we looked at VMS systems and also applications, is that with a VMS system, it used to take about half an hour for the system to crash, reboot, and fail again. Systems are much faster now, so it only takes 5 minutes to crash, reboot, and fail again. So we've speeded up the cascading of failures, we just haven't fixed the cascading of failures. The other thing we do is, we also looked at clusters, VMS clusters at those times. It's basically, you group things together, and technically wise, these are far more reliable systems because you have, multiple points of failures, and then you have things which can take its place. Unfortunately, they're more reliable until they fail, and then they're down for ages. And basically, what we always do is say, well, that's an exception, because there's a human error somewhere along the line. And we don't count that in our statistics. When we look at availability, we just ignore the exceptions. And the problem with here is the fact is 150 years ago, the railway people, if they saw a human error, they would actually figure out, well, is it the process is just too complex? The human's fine, but no human could actually handle this whole thing. And we actually still don't do this in computing. We actually still, as soon as we figure out it's a human error, then that we're relieved, because we can then sack the human, bring in another human in, and life will be fine until the next time, and then we do the same thing. So we then moved from hardware onto joining Microsoft, and we started looking at relationship between development and failures. And sadly went back to the sort of technology and tried to ignore the human element of this whole thing. And the first thing you then find is how many technology issues are actually independent of reliability. The first one is, you could argue about, but software language has very little impact on reliability. We haven't found any relationship. There was a paper whereby there's a website that they ask this problem, and then people write software and send it in, and then they test it. And they found that language is independent of failures. And the biggest cause of failures is people don't understand the problem. And if you don't understand the problem, it doesn't matter what language you write the solution is always wrong. Comments, in fact, the more comments is usually the less reliable the code, simply because when you actually have bugs in code, you write comments. So if you haven't had a bug in the code, you don't write comments. Code size, completely irrelevant. Used to be dribbling to me. Complexity, most complex code, you give it to your best people. People know it's complex. They actually take a lot of care over it. Most complex code is very reliable. The less complex code is less reliable. It's a bit like most mountain climbing accidents occur on the way down because people relax. Same idea with complexity. Coverage, similar to comments, you test bad code more than good code. So the higher the test coverage, the more failures in the system. Pre-release bugs, testers are usually driven by the number of bugs they find in the system. And if you measure people based on the number of bugs they find in the system, they will find a lot of bugs in the system irrespective of the quality of the code. So basically, pre-release bugs is no relationship to post-release failures. The factor we did find was churn, which is basically saying if you change code, it's more liable to fail, which is not really a sort of Nobel Prize-winning discovery. But we actually, we weren't that bad. We understood the complexity of the churn, not simply the actual activity. And it's really the relationship between churn on one level and churn on another piece of code, and the dependencies between those code. But you couldn't do predictive type analysis of the code. You could only do reactive. So you could basically say you've messed up, but you couldn't say you will mess up. And that's the thing we wanted to do. So we actually started looking at human factors. One of the things we looked at is code ownership. Is if you have a clear code which has clear ownership is more reliable than code which actually has diffused ownership, simply because you have ownership and responsibility in the same area. And it's the sort of proof of mythical mammon. We then started looking at things like distributed development. And these things become more complex because in Windows they moved things to Hyderabad. And we found that actually there was no lowering of reliability. But the reason for that was that they spent a lot of time handling the human aspects, and it wasn't a cost saving. A similar analysis in Avaya was that distributed development is disastrous. But what they did was offshore something on cost. So they sacked people in America, shoved the code over to India, and then was surprised to find that the Indians struggled to manage the code. So in all of these things, what you find is that it's actually, you can't make generic statements. You can only make specific statements about how people do things. Bug fixing, we have this phenomenal product studio which tracks bugs, and you define them by severity, and then there's prioritization. And what we find is that if your mate submits a bug, you fix that before somebody you don't know. We also discovered there's about 2 sites in Microsoft, and I don't know what they've done, but their bugs are never fixed. These people, keep submitting bugs and nobody fixes them. So they've obviously upset people somewhere along the line. So we're finally having to it's being forced us to actually look at these human factors. So one of the things we started doing, how we got into this was we started bringing these models, but we were very much focused on Windows, and our risk models were very good. We were very chuffed. And then we actually started working with Office and Exchange and Mobile and Link. And we then applied the models to these other products, and they were completely rubbish. Very embarrassing. And one of the things we looked at was, the first thing we did was simply fork the models. So we actually ended up with 5 models across each of the different product groups. But then we actually started to sit back and then say, well, why are they different? And what we discovered was that the original models had an awful lot of the domain knowledge, the way that the people in Windows developed the process. The tools they use is exactly the same in each of the different product groups. How they applied them, the focus they applied them was completely different. And one of the things you actually realize is that you have to differentiate between the tool use, the technology use, and the domains, information, how many people, like for instance, ownership of code. If you have common code, and that's separate from unique code. So there's an awful lot of things, and that realized that you can actually get generic models, but you have to separate out all of this information. So where we are today, we actually are I'm off tomorrow to Redmond, and we're working with them on looking at how they do branching in their software. But what we now do is we always work with more than one product group. And we're building analytics. We haven't got there yet, but we're building analytic engines to actually try to differentiate out, because the underlying trends are there on most of the products. So if we can actually have the engines do the underlying trends and separate out the domain knowledge, then we can get back into a generic model. You have to understand the intent of management and why they're doing things. That's another important thing. These metrics they generate, those metrics, okay, they're part of tools, but they inevitably end up being a measure of people. And people will gain metrics if those metrics affect their performance. I mean, I think Windows have now learned is never have a feature complete stage in June, because everyone's reviews are in June, and nobody will fail a feature in June if it ends in June. Whereas if it ends in November, people will be slightly more truthful. And there's nothing wrong with people gaming the system. They're usually gaming the system for good reasons, but you have to take that into account. And the other thing we do is we validate results by actually bringing in multiple product groups at the same time. So we actually have the results for Office and the results for Windows, and we discuss it with them both in the same thing. And we can then see commonality and also see where we've actually misinterpreted the data. And misinterpretation, we assume we're misinterpreting the data on the first cut anyway. And then it's sort of, we get the feedback, and then it allows us to build the models and improve the models. So, in summary, humans have been a pain in the backside. And will continue to be, I think. And not just AE1, it's development, it's testing, it's deployment, they all have the ability to undermine the work we're doing. And this finally forced us to at least accept it, and even having to talk to Richard, it's difficult. I think it's if you focus on technology, you end up addressing the symptoms rather than the root cause. I think is that we have to relearn what the railway industry learned 150 years ago, which is really that you can't just dismiss a human in the sense of saying is that, oh, he made a mistake. Humans make mistakes. It's really, was it a one-off mistake, or was it a generic issue? And basically, finally, I just say, if you ignore human errors at your peril, then if you're building a plane and you intend to fly it, I'm being very careful. So, thank you very much.
That's great. Thanks, Brendan. We'll take one question, I think, just in the interest of keeping things on time. Anybody have a question for Brendan? Andrew does.
So we've talked about this topic over the many years that you worked for me, and the thing about Microsoft and DEC is these are essentially technologies that evolve over time, and the next system is 80% the last one, plus a
Yeah.
few changes. How much of this do you think transfers into the world of, for example, the software house who are doing the big government contract for the NHS, electronic patient record or whatever? Do you think the same issues arise in that world, or is it a different game entirely?
I think, in fact, it's not a different game entirely, but I think they make it a different game entirely. I think the big issues that they have is they believe they understand the problem before they start. If you look at the way Windows works now, is they are very flexible on features. So they define the features, and then at each of the stages they reassess the features. And they can dump features depending upon time, but they also adjust them based on feedback from beta. Whereas I think is on the big government places, they actually believe they know the problem. And so they in the end, they specify the problem down to the last inch, and then it gives the contractors the ability to then up the price when they change the contract. So I think is that most of the things are common, and I think is for a lot of these things is if they show flexibility at the specification stage and admit they don't understand the problem, then they'll be far more successful in delivery.